the word networking. So basically, what it means is that it involves writing programs that communicate with each other, um, so that the programs running in two different computers are running in a network. They can communicate with each other. Even in general life, if somebody is saying that, okay, I'm doing networking, if he goes and joins some, conference or some party, he says, oh, I'm doing networking. It means he's trying to, build connection with other peoples and sharing his numbers, etc. So, the motivation behind this lecture is that there are several issues that arise when you do this, write your network programs, which you cannot see in writing a single program applications. So, in this lecture, we will give you an understanding of the basic Unix IO services provided by the operating systems, and how you can use these services to build applications such as writing your web clients and the web services, and how they communicate to each other over the internet. And you will also learn some different techniques to write the concurrent programs, such as your web server that can service multiple clients simultaneously. So these are all the things that we are going to see in this lecture today. So everything in the network applications, wherever, in everywhere, anytime you browse the web or send an email, or you're playing an online game, so you're always doing this, running this network application, even in the background unknowingly. So interestingly, all these network applications, they are based on the same basic programming models. They have all similar overall logical structures, and they rely on the same programming interfaces. So basically, the key idea is that every network application is based on the client server model. So some people refer to it as a client server transactions. With this model, an application consists of a server processes and one or more client processes. A server manages some resources, um, and it provides some service for its client to manipulate or to utilize those resources. So the fundamental operation in the client server model is the transaction, as you can see. So I'm going to show you how the transaction is performed in the client server environment in the figure below. So and note that these client and server processes is not a mandatory that they should be running on a different host. They can be running on the same host as well. So the first one is, at the first step, the client process will request the server. It initiates a transaction by sending a request to the server processes. For example, when a web browser needs a file, it sends a request to a web server. So then in the second step, the server which receives the request, it interprets it and manipulates its resources in the appropriate way. So for example, when a web server receives a request from the browser, it reads a disk file. And number three, the third step is actually that the server will send a response to the client based on the received request, and then waits for the next request to come so that it can serve to other clients. And the fourth step is that the client receives the response and manipulates it. For example, after a web browser receives a page from the server, it displays it on the screen for you. So you might have come across different web applications that you might have used. So this is the whole the logical transaction architecture that is running behind those applications. So it's client server transactions. So this picture shows you a hardware organization of a network host. So just like in your CPU, you have those IO bus running, and there are multiple things that are going to connect to this IO bus. You have a graphics adapter, you have CPUs, they are connected through IO bridge to the main memory, and you have a disk controller that is connected directly to your IO bus. So similarly, when you have a client and servers that often run on separate hosts, and communicate using the hardware and software resources of the computer network. So in such a case, to your host machine, whether it's a client machine or your server machine, a network is just another IO device that serve as a source and sink for data. For example, you can send or you can receive the data through that network adapter. So, what is actually a computer network? So in general, a network is defined as a hierarchical system, comprising of a lot of boxes and wires. Most importantly, how they are organized in a geographical proximity. Basically, location or this geographical proximity is one of the parameters that defines your network topology or your network, how your network should be named. For example, we have this system area network is often referred to as a SAN. It spans cluster or a machine room having a lot of machines. They are all stitched together via some switched Ethernet or Quadrex or QSW switches. So this forms a system area network. The second one is this local area network. You guys might be very familiar with this term, the LAN, local area network, and it spans a building or a campus. Like Sogang has its own LAN network. So in LAN, the Ethernet is most prominent example. So you can have like 10 gig or maybe 100 gig LAN, something like that. And the last one is the bigger one is WAN, this wide area network, and it spans country or like across the countries. And it has got typically high speed point to point phone lines that are a common example of this WAN. And an internet network. The internet actually is derived from the word internetwork. Is an interconnected set of networks. So the global IP internet update with the uppercase I is the most famous example of an internet, basically internetwork, lowercase I. So let's see how an internet is built from the ground up. So in upcoming slides, we will be dealing with all this internet stuff. So at the lowest level of this internet in the host machine, so we have this Ethernet segment. So an Ethernet segment consists of some wires, usually twisted pairs of wires, and a small box called the hub, as you can see in the figure above. We have a hub, and there are multiple hosts connecting to this hub. And this Ethernet segment typically spans small areas such as a room or a floor in a building, and each wire has got some maximum, bit bandwidth, megabit or gigabit, and typically in a host is almost like 100 megabit or 1 gigabit per second. And one end is attached to an adapter on the host, like network adapter, and the other end is attached to a port on the hub. And each Ethernet adapter has a globally unique 48-bit address, the MAC address, which is stored in the non-volatile memory on the adapter. So every adapter has got some non-volatile memory chip. And a host can send a chunk of bits called a frame or to any other host on the segment. But I have slavishly, copies every bit that it receives on each port to every other port. So thus every host sees every bit and frame, but the only destination host can actually read it. So note that the hubs are on their way out. So bridges, switches, routers, all these acting as a bridges, they're becoming cheap enough so that they can be replaced with the hubs. So the next level in this hierarchy is the bridge Ethernet segment. So previously we have seen that the multiple hosts are connecting to a single hub, but now we see that how multiple hubs are connected through these bridges in the middle of the figure. So multiple Ethernet segments, they can be connected into a larger local area networks called bridged Ethernets using a set of wires and small boxes called bridges. As you can see in the figure here, um, the slide shows quite a detailed depiction of these bridges and hubs, how they're being connected with the bandwidths written on top of. These bridge Ethernets can span entire building or campuses, and in a bridged Ethernet, some wires connect bridges to bridges, and other connect bridges to hubs. This bandwidth of the wires can be different. For example, in our case, in the figure here, the bridge to bridge wire has the X to Y bridge. They have got like 1 gigabit per second bandwidth, while the four hub bridges, they have got 100 megabit per second bandwidth. So bridges, they are cleverly, they're quite, clever and intelligent. So they can learn using distributed algorithms how they can, reach from port to port to send and receive the data, or how to copy the data, or how to selectively copy the frames from port to port. So, giving you guys a conceptual view of these lands. So to simplify those previous figures, so people usually tend to draw the hubs and bridges and the wires that connect them as a single horizontal line. So all the hosts, they will be connecting to a single horizontal line, and that horizontal line can be hubs or the bridges. So moving on to our next level, which is actually internets or internetworks. So the crucial property of an internet is that it can consist of different LANs and WANs with radically different and incompatible technologies, but somehow they are interconnected and they're stitched together to make a bigger internet. And each host is typically is physically connected to every other host in this network. So LAN 1, LAN 2, we have two different LANs in the picture, and we have two different WANs, and they're connected through these routers. And so any host on the LAN 1 can connect to any host on the LAN 2 via this wide area network. So note that these LANs can be of different technology, and they can be totally incompatible. For example, one might be using Ethernet, one might be using fiber channel or T1 links or InfiniBand and different kind of networks, network interconnects. So this is a logical structure of an internet. We have host, and there are some certain routers, and those routers are interconnected to each other, and somehow they are in some overlapping boundaries. So that's an ad hoc internet interconnection of networks. So there's no particular topology. Um, in a bigger pictures, in a bigger scales, you have to define the network, topologies, and there are vastly different routers, and they have got different versatile link capacities, how much data you can send or receive through these links. And you can send the packets from source to destination by hopping through the network. For example, host on the left can send the data from multiple routers to the host on the right, but it has to go through some algorithm so that you can find, that's where the shortest algorithm pathfinders algorithms, they come, and they tend to identify which is the shortest path to send data from left host to the right host. And of course different packets may take different routes on this picture. So the notion of an internet protocol. So we have seen internet, but it has got some internet protocol, and how the question arises that how is it possible to send the bits across incompatible LANs and these wide area networks, that the picture we have seen earlier, like 2 3 slides ago. So how it is possible for some source host to send database to another destination host across all of these incompatible networks? And the solution to this question, or the answer to this question, is very simple, that there's a layer of protocol software running on each host and the routers that smooths out actually, and that governs how host and routers should cooperate when they transfer data from network to network. So this software actually implements a protocol that governs how hosts and routers cooperate in order to transfer the data. And the protocol must define two basic capabilities. So the first, the two capabilities that are being provided by this internet protocol is it offers you a naming scheme, and the second thing, it provides you a delivery mechanism. So what does it mean by saying that it provides a naming scheme? So basically, we have a different LAN technologies. They have got different and incompatible ways of assigning addresses to the host. And the internet protocol, it smooths these differences, or um, it smooths these differences by defining a uniform format for host addresses. So each host is then assigned at least one of these internet addresses that are uniquely identifying it, or that uniquely identifies it. And what about this delivery mechanism? What does it, mean, or where does it stands for? So, same thing. We have different networking technologies, and they had got these different incompatible ways of encoding bits on these wires, and of packaging these bits into frames. And the internet protocol actually smooths these differences by defining a uniform way to bundle up these data bits to its discrete chunks called packets. So an internet protocol actually, it defines a standard transfer unit basically, which is the minimum granularity of sending and receiving data, is called the packets. And a packet consists of header and which contains a packet size, source and destination addresses, and our payload contains the data bits sent from the actual data, which is sent from the source host to the destination host. So these are two capabilities that internet protocol provides you. So the naming scheme and delivery mechanism. So whenever you are dealing with any kind of data, so these two are the must things that your protocol must provide. So next, we are going to see that how the transferring internet data through the encapsulation is performed between a server and the client, or between two host A and host B. So I hope you guys are familiar with the concept of encapsulation. So basically, when you are sending your data from one point to the second endpoint, so you always encapsulate your data. So the first, what happens is that the client on the host A actually, it invokes a system call that copies the data from client's virtual address space into the kernel buffer. So we have this client, we have protocol software, and then we've got this adapter on the host A. And the second is the step is actually this protocol, as we've seen previously. So it's a software that on the host A, it creates a frame by appending an internet header, and LAN one frame header is addressed to the router, and it then passes the frame to the adapter. And notice that the payload in as we see the internet packet is got data and frame header, and just got packet header. So data is actually the payload. Payload of the LAN one frame is an internet packet whose payload is actually user data, and this kind of encapsulation. So this is basically an encapsulation example. Is the fundamental insights of this internet working. So on the third step, we see that the LAN one adapter copies the frame to the network. So we see this LAN one adapter is copying the data onto this router. And this number four is that when the frame reaches the router's LAN one adapter reads it from the wire and passes it to the protocol software. So on the fifth step, we see that now the contribution from the LAN 2 and the host is going to start. So the router fetches the destination internet address from this packet, internet packet header, and use this as an index into routing table to determine where to forward the packet, which is the case, which in this case is actually the LAN 2 adapter. And the router then stripes off the old LAN 1 frame header and prepends a new LAN 2 frame header addressed to the host B. And then it passes the resulting frame to the adapter. So so in the six steps, we see that the router of the router's LAN2 adapter, it copies the data from copies the frame data to the network. So similarly, it's a contrary to the step three, the step six. And when we see the step seven, we see again is similar to the step two, that when the frame reaches this host B, actually the LAN2 in this picture, its adapter reads the frame from the wire and passes it to the protocol software. And finally, the protocol software is going to unbox the software, protocol software on the host B, LAN2. It stripes off the packet header and the frame header, and the protocol software eventually copy the resulting data into the server's virtual address space. And when the server invokes a system call to read the data, so that's how the whole transfer of data over the internet actually is being carried out through a router. So you see where the protocol software stands out, like where it contributes to transfer the data from one end to the other, and how the data is being copied in the router, and how router changes the frame header, and then it goes back to the destination address, and destination address, the protocol software running on the destination address, the destination host, it unboxes and then it gives the data back to the host. Um, Actually, there are several other issues. So we are just glossing over a number of important questions. That what if we have different networks have different maximum frame sizes? So what is the problems if the frames or the packet size they are different among different networks? So there are a lot of segmentation problems that can occur, and how do the routers they know where to forward the frames, and how are the routers informed when the network topology changes, basically the things that are stored in that routing table after a router. And what if the packets they get lost in the midway? Mm. Are there some other failures that let the packets get lost in the middle? um, actually, there are a bunch of other questions which are not going to be addressed in this lecture, but they're more probably you guys might come across some computer networking specialized course that will talk about all these issues, and you will learn a lot more there. So moving on to our next thing is global IP internet, internet with an uppercase I. So it's a most famous example of an internet. So it is the actually most successful implementation of an internet, and it existed in one form or another starting from 1969. And each internet host runs the software that implements basically that is based on this TCP/IP protocol family. And this IP Internet Protocol, it provides basic naming scheme and unreliable delivery capability of the packets, datagrams from host to host. Um, and of course, it provides some naming scheme and delivery mechanism that can send packets known as datagrams from one internet host to another host, and these datagram packets can be transferred from one process to other process, not supposedly every time from host to host, but also from process to process. So a server and the client can be running on the same host. It is possible. It's not mandatory that every client and server should be running on two different hosts, but they can run on the same machine or the same host. So we have this transmission control protocol TCP. It is used to provide these reliable byte streams from process to process over the connections, and all these they can be accessed via a mix of Unix file I/O and functions from the socket interfaces that we are going to cover later in the lecture. So how does actually programmer views this hardware and software organization of an internet application? So this picture actually gives you uh, uh, it gives you an overview of the software stack and the hardware stack of an internet application. So basically, on the top, on the client side, you have got this client user code, and the client actually use some system calls through this socket interface. And the socket in the kernel space, you have this TCP IP protocol running, and that TCP IP protocol is engaging your hardware interface via these interrupt system calls, and the request goes to your network adapter. So you've got these three layers: user code, and you have this kernel, and then you have a hardware and the firmware versions for those hardwares, and they're all connected through this your lower stack network adapter is connected to this global IP internet, basically internet, the network. And then on the server host, internet server host, you have this again same network adapter, and it's looking for the any request, incoming request, and then it passes the request back to the TCP IP protocol, and the protocol again unbox the data to the main server processes. So it's on the server end client, it's just the same hardware and software stack. So how a programmer views this internet, or how does a programmer looks at the internet? So there are two, three things that a programmer cares about this internet. So basically, the first thing is that all the hosts on the internet, they are mapped to a set of 32-bit IP addresses. So we have this IP address notation, 128.2 decimal notation, 203.179. And this the set of IP addresses, they are actually mapped to a set of identifiers called internet domain names. So like we have this sogang.ac.kr, that's actually a domain name, internet domain name for the IP address identification. And a process on one internet host can communicate with a process on another internet host over a connection. So you just need to build a connection, and then they can start communicating with each other. Uh, this, some side discussions that might give you some additional background about this. So we have this IP version 4 and IP version 6. The original protocol with its 32-bit addresses is known as Internet Protocol version 4. So which we often call IP4 or IPv4. So this is the most common IP address or IP Internet Protocol version being used even till today. So in 1996, the Internet Engineering Task Force, it's called IETF. You guys might have come across some articles on the internet saying IETF introduced some new Internet Protocol versions, or they have give some different statements about these networks. So they introduced a new Internet Protocol version IPv6 with 128-bit addresses. And actually, initially it was intended as a successor of IPv4. As of 2015, the vast majority of internet traffic is still being carried by IPv4, and only 4% of the users access these Google services using this IPv6, Internet Protocol version 6. But somehow, actually, we will focus on this Internet Protocol version 4, IPv4, and but we'll show you how to write the networking code that is protocol independent. So your source code, the program, network program that you will write, it's not supposed to be a protocol dependent. It should be a protocol independent. So the IP address. So what does it mean, or why we use these IP addresses? So IP address is an unsigned 32-bit integer which are stored in an IP address structure. So so it has got unsigned integer, 32-bit integer address, and it's called, we just store it as a data structure in the kernel, and these IP addresses are always stored in memory in network byte order. So basically the network byte order uses a big endian byte order, and big endian is actually when you encode the most significant bit first, and then you move in a descending order from higher to the lower. So that's called the big endian byte order. So actually, it's true in general for any integer transferred in a packet header from one machine to another. So the port number is always used to identify an internet connection. So whenever you are accessing some service, you need to put a port address that on which the server or the host server is listening to. And actually, there's a dotted decimal notation when you define your IP addresses. So these IP addresses are typically presented to humans in form of dotted decimal notation, so that it should be more intuitive and should be like a human readable format. So each byte is represented by its decimal value and separated by from the other bytes by period, by this full stop, the period dot. So for example, we have got this 128.2.194.242 is the dotted decimal representation of the IP address, this hexadecimal format. And similarly, you can use other ways, for example, other methods, get address information and get name information functions, which are described later, which you can convert between, you can move back and forth for IP addresses and these dotted decimal formats. So, how do you define your internet domains? So actually, the internet domains is a hierarchy which is represented as a tree. On the nodes of the tree, they represent domain names that are formed by the path back to the root. Um, the subtrees are referred to as a subdomains in this domain name tree, and the first level in the hierarchy is an unnamed root node. And the next level is the collection of first level domain names that are defined by a non-profit organization called ICANN. So I think it stands for Internet Corporation for Assigned Names and Numbers. So the common first level domain names include com, edu, gov, org, and that. And I guess in South Korea it's like AC dot kr. At the next level, there are second domain names such as dot edu. So it's like Sogang dot ac, which is assigned on a first come first served basis by various authorized agents of this ICANN organization. So after the second level, on the third level, and moving on from the third level to fourth and fifth and onwards, the organization is given privilege and given freedom to create its own third level domain names. Like we have this CSE Sogang AC.kr. So all these domain names the Sogang can create on its own. Okay, we have seen the domain name tree, but now moving on to DNS, how the internet people, they can look up this address, or how they all standardize naming uh, conventions on the internet. So the internet maintains a mapping between the IP addresses and domain names in a huge worldwide distributed database called DNS. So it's a domain naming system. So it's actually a database that maintains the mapping of IP addresses, mapping between the IP address and the domain name. So you have this both information. So you can either look up the IP address based on the domain name, or you can just, based on the IP address, you can look up the domain name, or based on the domain name, you can look up the IP address. So conceptually, a programmer can view the DNS database as a collection of millions of host entries. So each host entry defines the mapping between a set of domain names and IP addresses. So every host will have this mapping. There is some domain names and it has got some IP addresses. So the host can ask for anything. And in mathematical sense, a host entry is an equivalence class of our domain names and IP addresses. So what are the characteristics or the features of this DNS mapping and why it is actually required? So because this DNS mapping can explore the properties of DNS mapping using this NS lookup. So it's naming system lookup. So the output is actually edited for the brevity so that you can have more clarity. So each host has a locally defined domain name. For example, you have this local host on your system, and which is always mapped to a loopback address. Some people call it local IP, or local loopback address is most appropriate name for this IP. So it's 127.0.0.1. So if you do this NS lookup on your terminals, so you will see this IP coming back on your console, your terminal. And if you type this host name, so it's basically the first one is looking up domain name, and you are checking the IP of that domain. And the second one is actually you're looking for host name. So what is the host name running on this terminal? So if you use host name to determine the real domain name of the local host, then if you write host name, that will print the name of your host name of that machine. So, what are the properties of this DNS mapping? We are continuing. There are three different cases. So the first one is the simplest case. So in the simplest case, we've got this one-to-one mapping between a domain name and an IP address. So if you see NS lookup this domain name, and then we will get this IP address, fetched here. And in the second case, it's a bit more um, complicated, that you have got these multiple domain names which are mapped to the same IP address. So in the first line on this, in the second this terminal screen, you see nslookup cs.mit. But in the line beneath, you will see the two IPs printing against the same against the two different domain names. So in the second, we see nslookup eecs.mit. So they're two different domain names, but they've got the same IP. So the second one is kind of a bit complex case. Anyways, moving on to the further, more complex scenarios. So we see that there are multiple domain names that are mapped to different IP addresses. So, for example, the Twitter is being, backed by multiple set of IPs. So in other cases which are more general, they've got these multiple domain names that are mapped to the same set of multiple IP addresses. So you have got a set of IP addresses that are being linked to this domain name. And at the same time, we see there are some well domain names which are still not mapped to any IP addresses. So if you just type um, ics.cs.cmu.au, so you will not be able to find any kind of information against it, because this valid domain name is still not being used by any IP address, or is not being backed by any IP address. So that was about the domain name and DNS mapping properties. So now comes the internet connections. So how you make these internet connections. So internet clients and the servers, they communicate by sending and receiving stream of bytes over internet connections. And a connection is defined as an end-to-end point. It's a point-to-point communication in the sense that it connects a pair of processes. It has got this full duplex property in the sense that it can the data can flow in both directions at the same time simultaneously, and it is a reliable in a sense that bearing some catastrophic or some natural disaster failure, such as the cable cut by proverbial careless operator who's dealing with those um, cables. The stream of bytes sent to the source process is eventually received by the destination process in the same order it was not. So this is called these reliability problems. So it has to ensure that it should be a reliable, that the stream of bytes sent by the source is eventually received by the destination in the same order as it is being sent by the source. Similarly, a socket. So a socket is as an endpoint communication channel or a connection, and each socket has got its socket address that consists of an endpoint that consists of an IP internet address and a 16-bit integer port that is being identified um, by that is being denoted as a notation. We usually use it like IP address and the port, and they both are being used to identify to build a connection. And the port in the client socket address is assigned automatically by the kernel when the client makes a connection request, and it is known as the ephemeral port. And there are some well-known ports associated with some service provided by a server. For example, port 80 is associated with the web server. So we've got these well-known ports and service names. So the popular service names have permanently assigned well-known ports and corresponding well-known service names. For example, if you echo server port name 7/eco is being always being used by this server eco server, and if you ever use these SSH servers, so they're always in majority of the cases they use this 22. And for email services, SMTP, they usually use 25. And for any web service you run, if you run Apache Tomcat or some JBoss, Wildfly, so you will see in the browser, you always type HTTP and 80 port will be appended to it. And the mapping between the well-known ports and service names is contained in the file on the Linux machines like etc services on each Linux machine. So you can go and check, and even you can modify these services, these port numbers for these services. So DNS mappings, internet connections. Now we will see the morphology or the anatomy of actually a connection, that how a connection looks like to a programmer or to from the data structure point of view. So a connection is a uniquely identified by socket addresses of its two endpoints. This pair of socket address is known as the socket pair and is denoted by the tuple, as you can see in the slides below: CLI address, CLI port, client address, client port, and we have this server address, and server port. So they both connect to each other. So client has its own address and the port number, and the server is has its own IP and it has got its own port number. So all the connection is being built among each other through these two IP addresses and the ports. So in this case, one thing that you guys should need to know about this is that in the client address, we usually don't type the port number, but it's appended by, so it's an ephemeral port, so it's appended by the kernel with the IP when client wants to initiate a connection. So the server can respond back on this port number to connect to this client. So using these ports to identify the services. So given these client and server socket addresses, the connection between the client and server is uniquely identified by this socket pair and the ports. And this figure shows that how a web client and a web server, they communicate with each other. So we see the client host, it requests for some service on this IP server address and the port. So the web server, so the request goes into the server host, and there's a kernel, and then we have this web server running on this port 80, and we have got this eco server running on port 7. But because the client requested for the web server, so the request goes to the port 80 web server. So similarly, when the client requests for the eco server, so we see that the request goes directly to the eco server, and it doesn't follow that the upper figures web server the call path. Instead, the kernel will hook these eco server to the requested as a service to the requested client. So what is a socket interface? Because we have been seeing a lot the socket pair and the port, and but what does actually socket interface do, and what does it mean? How a programmer can utilize these socket interfaces to build the connections. So socket interface is a set of functions, the protocols that are used in conjunction with the Unix IO functions to build the network application. So these are basically kind of a key backbone when you write your network application. And it lets you connect between two hosts, and it has been implemented in most modern systems, including all Unix platforms as well as Windows and Macintosh, the Mac machines. So it was created in early 80s as a part of the original Berkeley distribution of the Unix that contained an early version of the Internet protocols, and it is available on all the modern systems, including these iOS, OS X, Android, almost every modern systems which is dealing with any kind of a network communication. They are implementing these socket interfaces. So socket, what is actually a socket at a very basic foundation? So to a kernel, a socket is an endpoint of communication, and to an application, a socket is a file descriptor that lets the application read or write from and to the network. So please remember that all the Unix IO devices, including networks, they're all modeled as a file. So in Linux, you see everything is just, being treated as a file, so you don't see any special device things. But if you plug a hard drive, SSD, or some USBs, you will always see files instead of these devices, because everything is just a file in Linux and Unix. And the clients and servers, they communicate with each other by reading from and writing to socket descriptors, which are actually the file descriptors connected. So our client has this client file descriptor, and the server, on the server end we have this server file descriptor. So you just read these file descriptors like you are reading or writing a channel of opening a file and reading and writing that inside the file. So the main distinction between these regular file IO and socket IO is that how application opens the socket descriptors. It's a little bit different from opening a file and opening the socket descriptor, this client FD, and in general the file descriptor. So what is actually the data structure being used for these socket address structures? So in generic socket addresses for address arguments, we've got this basic functionality like connect, bind, and accept. And these are functions that require these functions, they require a pointer to a protocol specific socket address structure. And the problem faced by the designers initially, designers of the socket interface, was that how they can define these functions to accept any kind of socket address structure. If you got incompatible networks, incompatible frames or packet sizes, then how you're going to deal with these kind of problems. So, but in today's the modern times, so we are using this generic white pointer, which did not exist in C at that time. So the solution was to define socket functions to expect a pointer to a generic socket address structure. So the address structure was like, we have got this protocol family, because we wanted to make it like protocol independent. So we just defined the protocol family, and we have got this socket address structure data, as you can see in the figure here. So the majority of the part are the socket address family, and then you define the family specific details. So we are using this type when we need to cast a socket address to a generic socket address structure. So you always need to have this kind of a family specific view, so that you can have import and socket internet address kind of thing. So whenever you're using that kind of a specific socket address, it is a must required to cast your socket address to this socket address structure, so that your function for functions that take socket address arguments, you can change it, you must cast it. Okay, this figure gives you an overview of the sockets interface in the context of a typical client and server transaction. So we will see how it works. So at first, you are going to, in the step one, you are going to start the server, and once the server is running, then the client will start, and the client will try to initiate a request. So it will open the client, open client file descriptor, and then the connect will try to connect to the server, and then we see that once the server accepts the request of the client, then we will have this exchange of data through different RI or different APIs, right? So we have this client and server session built on this step three box showing, and once it's done, then the client will disconnect, and server will drop the client IP address in the port in the connection, and then server keeps waiting for a new request to come in and listen to those requests. So the arguments to socket and connect are actually are generated for us automatically by this get address information. So it actually the key benefit of using this get address information method the function is that it allows our code to be clean and portable, and you don't have to um, define some absolute IP addresses or some hard code any of the addresses. So it gives us more portability and independence. So the get address function and the socket interface, they can seem somewhat daunting when you first learn about them. So this get address information is the modern way to convert the string representations of host names, host addresses, ports, and service names to socket address structures. So somehow this get address information actually replaced these obsolete methods that existed for very long previously, which are guest host by name and get server by name functions. One of the advantage of this get address information function is that it's a re-entrant, and it can be safely used by the threaded programs, and it allows us to write the portable protocol independent code, and it works with both internet protocol versions, IPv4 and IPv6. Somehow there are pros and cons. So the cons or the disadvantages of this get address information is that somehow it's a bit complex compared to the previous simplified get host name or get server by name methods. And fortunately a small number of users preference suffice in most cases, so you do not have multiple scenarios that deals this get address information. Okay, so when you're the picture shows the get address information method and free address information method and GISTR error method. So we see that this get address information has got this host name or address, a port or service name, and some address information pointers, and some or what are the output that you're going to get with these result pointers. So given host and service get address information returns results that points to a linked list of address information structures, each of which points to corresponding socket address structures, and it contains arguments for the socket interface functions. So you have got these helper functions, so you can perform, or you can invoke this free address information so that you can get the free you can free the entire linked list of the addresses. And you've got this GAISTR error, so you can convert the error code to an error message, so your application can give some error message which is more intuitive to use. Okay, so this is actually so after a client actually invokes this get address information, it walks this list trying each socket address in turn until the calls for the socket and the connect succeed the connection. So once the connection is established, um, so similarly a server is also also tries to that each socket address on the list until tries each socket address on the linked list until the call to a socket bind and bind succeed, and the descriptor is bound to a valid socket address. So that's how actually the data structure looks like. That we have got this address information structure, and and each of these entry is bind to a socket address structures. So when a client invokes, then client receives a linked list of the IP addresses. Then this one of the IP address, the client will bind these socket addresses, and then similarly the server will walk through the link list, and it will also try to bind one of the addresses to the socket, and then it will bind, and then the descriptor will be given to the server. So the server or the socket FD, which we call. So this is an address information structure. So it has got a lot of uh, parameters, or which you can call maybe the entries. So each address information structure returned by the get address information contains the function. It contains the arguments that can be passed directly to a socket function, and it also points to a socket address structure that can be passed directly to connect and bind function. So you have this specific socket address structure enclosed or encapsulated in this address info, so you can even directly pass these socket address structures, the socket addresses. So host and service conversion. So we have got this get name information. So actually, it's like an inverse or the opposite of the get address information, which converts a socket address to the corresponding host and service. It replaces obsolete get host by address and get server by port functions. So it is also some advantages. It's a re-entrant, and it's a protocol independent, so you don't have to define any protocol when you invoke this get name information. So this example actually is a simple program which can be called which calls the host information that uses internally the get address information and get name information to display the mapping of a domain name to its associated IP addresses. So first of all, we are going to initialize the hint structure that is given to its that it so that the get address information returns the addresses as we want. So we see that in the hint start AI family, we pass the AFI net and the socket stream, and then we call this get address information. So this get address information is going to return some linked list of the addresses we want. And then we see that after the call to the get address information, we will walk the list of we will loop the address information structures, and we will use get name info to convert each of the socket addresses to a dotted decimal address string. So get name info, and we will be passing these AI addresses there. And after walking the list, we are careful to free it by calling the. We should be very careful about this. Like you should call this free address information, so you can clean up the mess, all the linked list mess that you have initially created. So although for this simple program, it is not strictly necessary to call this free address information, but it's a best practice to apply this free address information when you write your program with of this conversion kind of types, get address and get name conversions. So when we run a host information, we can see the IP address is running behind. Let's say you run host information localhost, you will see this IP. When you run the host information and you pass some domain name, so you are gonna see a little bit different IP. Similarly, if you pass some other domain name which has got this multiple set of IPs hooked to a same address, so you are going to see set of IP addresses. So this is actually the domain naming system. We have seen that you have got the simple case, you have got multiple case, you have got a list of IPs. Uh, Actually, it's a more generic case. That's twitter.com. So you have got a list of IPs, a set of IP addresses that are being mapped to this domain name. Okay, students, that's it. We're done for today. And thank you so much for listening to my lecture. And please feel free to give me some questions if you guys have any confusions or misunderstandings. Or you can even post me an email. I will ask the Changu, the TA, to post my email even on that your e-class. So yeah, please feel free to ask me any question if you have. So in the next lecture, you are going to um, learn about this, how you can use this get address information for host and service conversions, and how you will actually learn to write the client and server programs, and how you can write your own web servers. I think that will be covered by Professor Youngji Kim. So that's it. Thanks. All right. I see a lot of thanks from you guys, and thank you so much, guys. Okay. Thanks, everyone. Take care. Bye.